So this section, we're going to be talking about projectile motion, which is, in other words, free flight motion of a projectile. And what we're going to do is we're going to study this motion through use of rectangular components. So we're going to break this up into X and Y. So what we're going to say is we're going to say that our X is in the positive direction this way, and the Y is in the positive direction up. So if we look at this picture here, the red ball is dropped with no initial velocity in the X direction. It's just dropped right straight down, and the only thing acting on it is the acceleration due to gravity. So the acceleration is equal to minus, we're going to say minus g, because that's going down, which is opposite to our y direction. Now the yellow ball, on the other hand, has some initial velocity in the x direction. So it has some initial velocity in the x direction, but it's also acted upon by acceleration due to gravity, which is a equals minus g. Now look at what the difference is. This picture is really an interesting snapshot of what happens in projectile motion. So the red ball, you can see these horizontal lines are different instances. It's the different vertical displacement. So between the two horizontal lines is the vertical displacement. And what you can see is between the red and the yellow, at each time interval, they have the same displacement. So that shows that they both are acted upon by the negative gravitational acceleration that acts downward. Now, the other thing that you can see is in this yellow ball, the vertical lines that are showing, you can see that at each vertical line, so at each displacement, the horizontal displacement is exactly the same. So what that tells us is that the velocity in the x direction is constant. This is really important. So in projectile motion, the velocity in the x direction is constant. So our initial velocity, v sub 0x, must equal our final velocity in the x direction. Now that is not necessarily true in the y direction. And we're going to show you using our equations that we had created last section when we were talking about rectilinear kinematics. We have constant acceleration equations. Well, those constant acceleration equations are clearly going to be used here in projectile motion because that's exactly what we have. We have acceleration due to gravity is constant. So this picture just shows, our xy coordinates. And right here on our picture, right here, this shows the initial position of our projectile. So the blue dot represents the particle, and it has an initial velocity of v sub 0. We can break that into x components, so v sub 0 in the x direction, v sub 0 in the y direction. And you can see this path that it takes, this blue path, is acted upon by acceleration due to gravity the entire time. It is subjected to that. But that is the only force, the force of weight is the only force that acts on this particle. And then here, this is the final position of our particle. So you see it has a velocity, final velocity, and we can break that into the velocity in the x direction and the velocity in the y direction. Now, you should always note that velocity, this is something that's going to be very important as we work through our dynamics problems throughout the semester. Velocity is always tangent to the path. Okay, so that's very, very important to remember. You can see how the velocity, the way they're showing it in the picture, is tangent to the path. And you can also see that these are the positions. So this is our initial position in the x direction. This is our initial position in the y direction. And this is our final position in the x direction. And this is our final position in the y direction. Now the acceleration due to gravity in the metric system, acceleration is equal to 9.81 meters per second squared. And acceleration in the standard or English system, 32.2 feet per second squared. And this is very important that you remember this and that you memorize this and are able to recognize when to use which one. Okay, so make sure you understand your problem, which units you're working in, so that you can appropriately apply the correct acceleration due to gravity. So what we're going to do is we're going to break up our projectile motion into horizontal and vertical motion. Now in the horizontal direction, we said that there is constant velocity, right? So our initial velocity in the x direction must equal our final velocity in the x direction. So if we have constant velocity, then acceleration must be 0 in the x direction. Okay, so all we have is acceleration due to gravity in the y direction. So this is equal to g. Okay, so if we go back to our constant acceleration equations, if we know that our initial velocity is equal to our final velocity, then what we can use is we can use the one equation that relates position and velocity. And this was the s is equal to s sub 0 plus v0 times t plus 1/2 ac t squared. That was one of the equations that we derived. So now what we're going to do is we're going to replace the s's with x, because x is our horizontal direction. So we're going to say x is equal to x sub 0 plus the initial velocity in the x direction times t. And this is 0 because we don't have any acceleration in the x direction. So this is our horizontal motion formula. So our final position in the x direction equals our initial position in the x direction plus our initial velocity in the x direction times time. And in the vertical direction, we have our vertical motion, and we cannot say that the velocity is constant, right, in the y direction. So we actually have our equation. We have v is equal to v sub 0 plus act, and we're going to make this in the y direction. So vy, so that's our final velocity in the y direction, is equal to our initial velocity in the y direction plus act. Okay, so that's one equation that we can use. So this is one equation for the horizontal. This is a second equation we could use in the vertical direction. And then we can use our position. So this is going to be for the y direction. We can bring the same thing over. So now instead of x, we're going to use y. So final y is equal to initial y plus our initial v0y times t plus 1/2 ac t squared. And our ac is going to be acceleration due to gravity. So this is ac in the y direction. Okay, so that's another equation that we have. So it's a third equation. And then our fourth equation is our relationship between acceleration, position, and velocity. So that's vy squared is equal to v0, initial velocity in the y direction, squared, plus 2 ac in the y direction, times final position in the y minus initial position in the y. So that's a fourth equation that we have. Now, okay, so as a summary, here are the vertical motion equations that you can choose from, what we had just discussed on the last page. And it's important to note that the direction of your axes is really important. So if I'm showing the y, positive y going vertically up, then acceleration due to gravity, which is ACY, must be negative. So when I replace my ACY in these equations with the acceleration due to gravity, I must put a negative sign in there. So it's very important that you use the coordinate axes to specify the appropriate positive and negative directions. The other part that is very, very important is what I wrote down here at the bottom. Can only use 2 of these equations along with the horizontal motion equation. And if you think about that, it makes sense because how did we figure out this last equation? We derived this last equation, this one right here. We derived this one from the other 2. So we can only use 2 of these equations because we need to have independent equations. So this third one is dependent on the other 2. So we cannot use all 3 because then they would therefore not be independent of each other. We can only use 2 of them.